Okay, so we're going to do our last problem now. And this is a rack and pinion, kind of like a steering concept, except it's a little more industrial. So here, check this out. We have a inertia, all right, and it's got some friction along the outside, so that'll oppose motion. We have an applied torque. We're going clockwise positive, okay. Here we have this long rod, which we'll model as a spring, okay? And so as we move this in the positive direction, that will be opposed by the spring. On the other hand, as we uh, twist this pinion here in a positive direction, that'll tend to turn this in a positive direction, all right? Now, if you look at this, as you try to twist this in the positive direction, the teeth in the rack will oppose it. So there'll be an opposing torque of F times R associated with this pinion. At the same token, that force that pushes back here will be the driving force on the rack, okay, which is opposed by damping along the bottom. All right, so we want to put together a model for that. So it starts with free body diagrams, as it always should. All right, so here we had, maybe we'll just leave this here. So looking at this from the outside, we have an applied torque coming here. Here's clockwise positive, all right? And so we have B theta dot opposing. As you twist this positive, this will oppose. And then as you twist this positive, okay, that spring will oppose. So that's minus K. This is opposing, so that here there'd be positive. The sign looks positive, K theta. The minus would indicate going clockwise. Now, holding this still, if you take this pinion and give this a twist, right, that would then have a torque going the other way. So relative to this picture, minus K theta A, because we've already declared that direction for the arrow. All right, well, once you've done that, so here's what we just said. We can just read it off the picture. J theta double dot equals tau A positive minus B1 theta dot minus K theta minus theta A here. And we can do the next group, bring all the thetas together. We have the following, and of course you can convert that into Laplace very easily. Moving on to that pinion. All right, here's the picture. So as the pinion goes in the clockwise direction, positive for these will both be in the same direction, it'll be opposed at the rack. There'll be a tooth force, F, and then the terms of that'll oppose it, times R, that's the opposing torque. And then we have, as this goes in a positive direction, K theta A, that'll oppose it. But if this turns in a positive direction, it would help it. So here's negative, and so we have a minus K theta that's going the other way. All right, gather terms. All right, the pinion is treated as massless, so we have a 0 there. And so we have going minus K theta A minus theta, just reading it off the free body diagram, minus FR. So we can just solve for this right here. Then that force that drives, that causes this opposition torque, is the force, the same force going the other way, is what makes the pinion, the rack, want to move, which is opposed by B x dot. So mx double dot equals the force in the positive direction minus the damping in the other. Okay, so to reduce this down then, we would have, let's just look at our algebra. So we can take this equation and convert it. All the dots just become s to various powers, s squared, s. All right, so here we have this relationship. Okay, this will become equation 2, which this is put into Laplace form, which really isn't any great mystery. Okay, but we can solve here for what f is. So solving for f, move that r to the other side. We have that relationship. I'm calling that equation 2a. Then equation 3, here's the force driving this thing. So we have from here ms squared plus bs times x of s equals f of s. Now we can start to make some substitutions. And so you'll see I say take 2a, that's this thing, stick it into 3. I don't care about f of s. Okay, I have an applied torque, and then I have a motion in the end. I care about x, and then this is the input. Okay, so here I have the x, and the f I want to get rid of. I'm going to bring this down into here and express it in terms of theta. Okay, now I will notice, because I'm building this up, that x equals r theta a. So I'm trying to build up transfer functions, and then I can always substitute back in, but x of s equals r theta a of s. Okay, so I can go in here. Let's see, where do I want to go in? I can bring this r up and then put r theta a of s in here, and that gives me r squared theta a equals k theta minus theta a. Now I can bring the theta a to the other side, theta a, so I group all those things together, and now I can have a transfer function relating theta a and theta. All right, so I'm going to call theta, all right, this is the input here, relative to the pinion position, this. Okay, so I've given it a name, so I don't have to keep tracking all these symbols. All right, so now let's look at this equation 1 here. Here's theta. Okay, I can rewrite theta because here's theta a. So here's theta to theta a. If I multiply through by theta a, I have an expression for theta. That's what I have here. So I'm going to substitute transfer function 1 times theta a equals TF, the applied torque, plus k theta a. Ooh, I bring this to the other side. And I now have a transfer function relating the pinion position, angular position to the applied torque is this, just manipulating all this. And see how much easier it is just to write TF1 than all of this plus all of that. All right, but here's theta A. Ooh, if I just multiply that by r, I get x. Stick that in, and so I have x relative to the input torque is r times TF2, where TF2 is all of this stuff. And there's the answer to the problem. All right. We are now ready to begin electrical systems. So that is what's coming next. Talk to you soon.